Okay, hello everyone. So till now we have discussed two methods. By utilizing those two methods, we can convert an automata into a regular expression. So the very first method we have discussed state elimination method, and another method we have discussed Arden's theorem or Arden's method. So let's utilize the Arden's method and try to convert a given automata into a regular expression. So how we can convert? Let's try to understand how this method works. So there are certain number of steps. First, look at the step and then we convert this into the regular expression. So the number of steps, the very first thing, whatever the automata you are trying to convert into a regular expression, that automata should not be having any null transition. So if there is any null transition, first we need to remove the null transition. And how to remove the null transition, that I have already clarified in my previous videos. So you can check it. Okay. Now, I believe that whatever the automata has given, it does not have any null transition. So the very first step is okay, there's not a problem, it is done. Now the next thing is find characteristic equation for each state. So what is the characteristic equation actually? In characteristic equation, we focus on the input arrow to a state. So we try to write a kind of expression. We try to express that how we can reach to that particular state. Okay. So what are the characteristic of a particular state? How machine can reach to that particular state, that define the characteristic equation, right? Then the third step, for initial state in the characteristic equation, we add epsilon also or null also. So what is epsilon or null? Why we add in the characteristic equation? So in order to understand this clearly, what is the characteristic equation? I'm writing, let's say this is state Q1. So if I want to write the characteristic equation of Q1, that Q1 can be achieved from Q2 by following B, not Q2, Q0 by following B, or from Q1 by following B also, this state can be achieved. So there are only two input arrows. One is this, another is this. By looking at the input arrows, we can write the characteristic equation, right? So for Q1, we can write Q0B and Q1B, right? From Q0 by following B, we can reach Q1. From Q1 by following B, we can reach Q1. So this is the characteristic equation. When we write the characteristic equation of Q0, so if I want to write the characteristic equation of Q0, the very first thing we can write for this arrow like this loop. So we can say Q0 followed by A. If you use this, you will be on Q0 only. Or there is another input like from here. So we can write from Q2. If B you are traversing, then you will reach Q0. There is no other input arrow to the Q0, but Q0 is the initial state. So here we are mentioning these for the initial state characteristic equation, add epsilon. So we have to add epsilon because it depicts that without taking any input, you can reach to a state that is Q0, that is your initial state. So if we write the equation for, let's say, Q2, the characteristic equation, Q2 is having one and two input arrows. So we can write Q1A or Q2A, right? So these equation we can write. Now what we try to do and how Arden's method will help us to ultimately conclude the equivalent regular expression for this given automata. Now Arden's method I'm writing here. So what is Arden's actually? We have seen R is a regular expression. It is given like if it is Q plus RP is given, then it will give a unique solution. R is equal to QP asterisk or cleans closure. So that is Arden's method that we have discussed and proved in the previous class, right? And there is a condition. This P should not be generating null. So it should not be generating null, right? So now let's start applying this particular format to the given equation. So if we try to apply on Q0, Q0 doesn't have only two terms. There are three terms. So for the moment, we just omit the Q0. Let's try to apply on Q1 or Q2. Okay. So the very first thing we focus Q1. So if I consider Q1 as R, let's say. So this is representing, let's say, R. Here Q1, so again it is representing R. Along with R, there is P. So that means this B will represent P. And B obviously cannot be 0 because B is the literal, right? And this remaining thing we can compare with Q. So if this is the scenario, because of Arden's, what we can write Q1 is equal to Q1 means R, R is equal to Q, Q means Q0 B. The Q is represented by Q0 B, followed by P asterisk. P is B only. So this we can write. I hope you are getting it, right? So not a problem. You can easily get this. Similarly, if you can apply this particular thing, if you want to apply this particular thing on this particular equation, Arden's method, you can easily apply. So in terms of Q2, you can write Q2 is equal to, so in this case, if you want to compare, this Q2 we will be comparing with R. So let's say Q2 is R. This A will represent P, and obviously A cannot be null because it is a literal. And the remaining thing you need to compare with Q. So if you want to write this equation by using Arden's theorem, you can write Q2 is equal to uh, RP asterisk. So R is Q2 only. No, this is RP asterisk, QP asterisk, right? So this is Q1, A, this is Q, and P star. P star means A star. So I hope it is clear how we can convert this and how we can utilize these expressions further. So I hope this is okay. How we can, but what we generally do, we don't try to apply Arden's like in this manner. So if you have converted already one thing, that thing we can replace in another equation. Okay. So if we already get the equation of, let's say, Q1, we can replace this Q1 here. Okay. And that Q2 we can replace there. So in that way we can find out, right? So if you already got the equation of Q1, in the equation of Q2 you can replace. In the equation of Q2 you can replace, right? So let me replace that. The equation which we get from here, let's say this is equation 1. Based on this equation, I am just passing this value Q1, let's say here. Okay. So if we want to pass this value here, what it will give us? It will give us, let's say, Q2 is equal to, instead of Q1 you write Q0 B star followed by A, because this A is there, plus Q2 A, right? So this will be converted like this. Now if you want to apply Arden's, again we can apply Arden's. So this Q2 we can compare with R. This Q2 is R. That means this A is representing P, and this remaining thing can be Q. So if we write by applying R, what we will get? The equation of Q2, if we want to write, we can write Q. Q means Q0, B asterisk, A, and then followed by P asterisk. P means A, so A star. So that we can get the equation of Q2. Now, if this is I'm considering, let's say, second equation. If we want to put this value of Q2 in this, so if I write here, let's say Q0 is equal to Q0 A is there, plus, instead of Q2, I'm writing Q0 B asterisk, A asterisk, right? Followed by B, because this B is there, plus epsilon. So what exactly we will get here? We will get, if we take this Q0 as common as out, then we will get A plus Q0, and Q0 is already, then B asterisk, A asterisk plus epsilon. Okay. So if we want to apply Arden's on this Q0 will start representing R. Along with R, we write P, so this thing will represent P, and the remaining thing will be Q. And remember one thing, there is a restriction. P should not be null. P should not be null. P should not be generating null. But there's no such a restriction on Q. So Q can be epsilon or null also, right? So if we want to write the equation by applying Arden's theorem or Arden's method, what it will give? R is equal to QP asterisk. So Q is null. P asterisk means A or B asterisk, A asterisk, asterisk, right? So if we represent this thing, this null coordinated with this thing will give you A or B asterisk, A asterisk, whole asterisk. So this is the equation of Q0, right? Now we cannot say this is the final regular expression of this particular automata. This is just I was trying to depict how we can convert. So the last step which I have mentioned here, express the final state by regular expression. So we need to write the regular expression for final state, and in this automata, the final state is Q2. So if I focus here, Q2 is having Q2 is having an equation that is Q0 in terms of Q0. So if I write this particular equation here instead of Q0, if I replace this will get a regular expression, right? This will get a regular expression. And by applying the Arden's theorem, we can get a final equation. We can get a final equation. So let me clear this. Now, if I write Q2 is equal to, my Q2 is this equation 2. My Q2 is this equation 2. So rather than going to this particular equation, I can just utilize this. So now I have the value of Q0. My Q0 is A or B asterisk, A asterisk, whole asterisk, right? And followed by this B asterisk, A asterisk. Okay. So if this is the equation of your final state, the characteristic equation, then we can conclude that this regular this automata can be converted into this regular expression. So this regular expression is the equivalent regular expression to the given automata. I hope the steps are clear. I just quickly revise these steps. First, look at whether there is any null transition or not. There should not be. If there is any null transition, remove it. Then write the characteristic equation for each and every state. Include epsilon for initial state. And finally, write the equation for final state. Whatever the regular expression will be derived for final state, that will be the ultimate required regular expression for that automata. So I hope this is clear. Thank you everybody for connecting. We will solve few more problems. See you in the next class. Take care.